Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The dawn of the 20th century presented physics with a significant conceptual challenge. The refined, predictable structure of Newtonian mechanics, highly effective in detailing planetary motion and projectile paths, revealed limitations when encountering the complexities of electromagnetism and the peculiar characteristics of light. A core problem surfaced: how to articulate physical laws in a way that maintained consistency, regardless of an observer's movement or the chosen reference frame. This pursuit of invariance of the descriptive method for physical reality that was free from subjective viewpoints served as the intellectual environment where Tullio Levi-Civita developed some of his most lasting achievements. The geometric language, prevalent then, based on Euclidean space and Cartesian coordinates, proved increasingly insufficient. While adept at describing flat regions, it faltered when accommodating the non-Euclidean geometries that mathematicians were exploring and which proved vital for a more profound comprehension of physical events. The very structure of space and time, as conceived by scholars such as Bernhard Riemann, was potentially curved, distorted by the presence of mass and energy. Explaining the behavior and transformations of physical quantities within these curved spaces required a fundamental shift from established techniques. Consider the basic operation of differentiation within Euclidean space. The derivative of a function indicating its rate of change is uncomplicated. However, when transitioning to a curved space, the concept of a straight line or direction becomes more intricate. If one were to take a vector, perhaps representing velocity, and transport it along a curved path, its orientation would intrinsically alter relative to a stable external reference. The subsequent inquiry was: how does one define the rate of change of a vector to encompass this inherent directional alteration, an alteration dictated by the space's geometry? Applying standard calculus rules, which are inherently linked to a fixed, flat framework, would produce outcomes dependent on the selected coordinate system, thereby contradicting the principle of invariance that physicists aimed to uphold. This dilemma formed the intellectual context for Levi-Civita, collaborating with his mentor Gregorio Ricci-Bastro to introduce a groundbreaking mathematical system, tensor calculus. Their seminal work, particularly the development of the concept of covariant differentiation, provided the indispensable tools to navigate these complex geometric landscapes. They recognized that to speak of physical laws in a coordinate-independent manner, one needed a way to differentiate geometric objects such as vectors and tensors that accounted for the underlying curvature of space. The problem of differentiating a vector in a curved space can be understood by imagining transporting a vector along a path. If the space is curved, the vector, when parallel transported, will generally not end up pointing in the same direction as it would if it were simply slid along without regard for the space's curvature. The difference between the vector at the end of the path and the vector that would have resulted from a straight line parallel transport is a manifestation of the space's curvature. Levi-Civita's brilliant insight was to formalize this concept. He devised a method, the covariant derivative, which essentially measures the rate of change of a tensor field along a given direction, taking into full account the way the coordinate system itself changes from point to point due to the space's curvature. This covariant derivative was a fundamentally new operation. It introduced the concept of a connection, a mathematical object that encodes how vectors are parallel transported in a given space. The Levi-Civita connection, specifically, is the unique connection that preserves the metric of the space, meaning it respects the distances and angles defined by the space's geometry. This property was crucial, as it ensured that the geometric relationships between points were maintained during parallel transport. The significance of this development cannot be overstated. It provided physicists with a robust and elegant framework for expressing physical laws in a way that was independent of the observer's frame of reference or the particular coordinate system used to describe the space. Tensor calculus allowed for the formulation of equations that were intrinsically geometric, their form remaining constant regardless of the representation. This was precisely what was needed to tackle the grand challenges of gravity and electromagnetism. The ability to describe how quantities changed intrinsically within a curved space without reference to external, flat coordinates was the missing piece for Albert Einstein's developing theory of general relativity. Einstein's revolutionary idea was that gravity itself was a manifestation of the curvature of spacetime caused by the presence of mass and energy. To translate this profound physical insight into a mathematical theory, he required a language capable of describing this curvature and its effects. Tensor calculus, with its covariant differentiation and invariant formulation, provided that language. The equations that govern the motion of objects in spacetime, and indeed the equations that describe how spacetime itself is curved by matter and energy, are formulated using tensors and their covariant derivatives. Without Levi-Civita's rigorous mathematical groundwork, Einstein's vision of gravity as geometry would have remained an eloquent but unquantifiable hypothesis. The machinery he developed allowed for the precise calculation of how light bends around massive objects, the precise prediction of Mercury's anomalous orbit, and a conceptual foundation for understanding phenomena like black holes and gravitational waves. The enduring legacy of Levi-Civita's work in this domain lies in its absolute centrality to modern theoretical physics and mathematics. Tensor calculus is confined to the realm of abstract geometry. It is the fundamental language of differential geometry, a field that underpins much of contemporary physics, from quantum field theory to cosmology. It is also a vital tool in fields as diverse as continuum mechanics, where it describes the deformation of materials, and engineering, where it is used in areas like robotics and computer graphics. The intrinsic, coordinate-free approach it offers provides a clarity and universality that continues to inspire and enable new scientific discovery. It represents a triumph of abstract mathematical thought, providing the essential framework for understanding the very geometry of the universe. The realm of geometry, for centuries, grappled with the challenge of describing physical phenomena within spaces that deviated from the familiar Euclidean plane. As mathematicians and physicists explored the implications of curved spaces, a pressing need arose for a system capable of handling geometric quantities and their transformations in a manner that transcended the arbitrary choices of coordinate systems. The very act of differentiating geometric objects, of describing how quantities change from point to point in a curved manifold, proved a formidable hurdle. Without a universally applicable method, the formulation of physical laws became intrinsically tied to specific choices of coordinates, obscuring their fundamental, inherent nature. Within this intellectual landscape, Tullio Levi-Civita, building upon the foundational insights of Gregorio Ricci-Bastro, provided a revolutionary solution to the formal development of tensor calculus. This mathematical framework offered a language and a methodology for understanding and manipulating geometric quantities in a coordinate-independent fashion. The core of this development lay in the concept of the covariant derivative, a sophisticated tool that allowed for the differentiation of geometric objects such as vectors and tensors in a way that accounted for the underlying curvature of the space, yielding a result that was invariant. The covariant derivative reflected the intrinsic geometric properties of the manifold, a departure from simple partial derivatives sensitive to the chosen coordinate grid. Levi-Civita's work elucidated how to define parallel transport, the process of moving a vector along a curve in such a way that it remains parallel to itself according to the intrinsic geometry of the space. This concept is crucial because in a curved space, a vector moved along a closed loop might not return to its original orientation. The covariant derivative provided the precise mathematical machinery to define this parallel transport, ensuring that the process was path independent for certain types of connections. This ability to define parallel transport without reference to specific coordinates was a profound achievement, offering a way to compare geometric quantities at different points in a consistent and meaningful manner. The The introduction of the covariant derivative and the rigorous treatment of parallel transport provided the essential mathematical apparatus for describing curvature itself. Curvature, in this context, is an intrinsic property of the manifold that dictates how geometric relationships change from point to point. Levi-Civitas, tensors, and their calculus offered a means to quantify this curvature, to express it in equations that held true irrespective of the observer's coordinate system. The pursuit of intrinsic properties and invariant formulations of physical laws was paramount. It meant that the fundamental equations governing the universe would reflect the underlying reality of the geometry itself, rather than being beholden to the particular way we chose to describe it. The impact of this work was immediate and far-reaching. Tensor calculus provided the essential language for differential geometry, a field that blossomed in the wake of Levi-Civitas' contributions. Tensor calculus provided a powerful language for describing geometric structures across diverse physical and mathematical domains. Navigating the intricacies of curved spaces presented unique challenges, particularly when attempting to compare vectors located at different points on a flat surface. Transporting a vector parallel to itself is a simple operation. Its orientation remains unchanged regardless of the path taken. Consider a vector drawn on a sheet of paper. Slide it across the paper, and its direction relative to the paper's grid stays constant. The notion of parallelism seems absolute. A situation changes dramatically on a curved manifold, such as the surface of a sphere. Imagine attempting to transport a vector parallel to itself along a path on the sphere's surface. If you move a vector initially pointing north from the equator up to the North Pole, then transport it along a line of longitude to another point on the equator, and finally move it back to the starting point along the equator, the vector's final orientation will generally differ from its initial orientation. This path dependence reveals that parallelism in curved spaces is a far more subtle concept than in flat Euclidean geometry. A universally agreed upon definition for vector parallelism between points where the connecting path held significance remained elusive. The elusiveness of a consistent rule for parallel transport into the development of differential geometry and its application to physics in curved settings. Tullio Levi-Civita confronted this fundamental problem directly. This profound insight, developed in collaboration with Gregorio Rick-Bastro, concerned the formalization of this idea of parallel transport. They sought a method to define how a vector's components change as it is moved infinitesimally from one point to an adjacent one along a specific direction on the manifold. This change should be intrinsic to the geometry of the space itself, independent of the particular coordinate system chosen to describe it. The key was to find a rule for differentiation that accounted for the curvature of the space, a rule that extended the familiar concept of directional derivatives from flat space to curved manifolds. Levi-Civita's unique solution involved introducing what is now universally known as the Levi-Civita connection. This mathematical object provides precisely the required rule for parallel transport and covariant differentiation on a Riemannian manifold. A Riemannian manifold is a space equipped with a metric tensor, which defines the inner product of vectors at each point, thereby specifying lengths and angles. The metric tensor essentially encodes the local geometry of the space, telling us how distances are measured. Levi-Civita demonstrated that for any given Riemannian manifold, a singular connection exists possessing two crucial properties that is torsion-free and compatible with metric. Being torsion-free implies a certain symmetry property related to the commutation of covariant derivatives. Geometrically, it ensures that infinitesimally small parallelograms constructed by transporting vectors along their edges close properly. This property aligns with the intuitive notion of a space exhibiting smooth integration at the infinitesimal level, a characteristic of the geometry described by metric tensor. Compatibility with the metric is a second, equally vital property. It means that parallel transport preserves the lengths of vectors and the angles between them. If you transport two vectors parallelly along a path, their inner product, and thus their lengths and the cosine of the angle between them, remain constant. This property is deeply intuitive for a notion of parallel transport in a space where the metric defines the geometry. It ensures that the act of moving a vector parallelly respects the fundamental geometric structure provided by the metric. Levi-Civita proved that these two properties, being torsion-free and compatible with the metric, uniquely determine the connection on a Riemannian manifold. This uniqueness is profoundly significant. It means that the geometry of the space, as defined by its metric, inherently dictates a singular, natural way to define parallel transport in covariant differentiation. The metric specification yields a unique outcome once it is specified. This established the connection as a fundamental, intrinsic feature of the space's geometry, a concept previously potentially ambiguous. The components of the Levi-Civita connection in a given coordinate system are known as the Christoffel symbols. The connection, while dependent on the chosen coordinates, is a tensor object. This signifies its existence independent of the coordinate system, transforming in a specific way under coordinate changes to preserve its intrinsic meaning. Levi-Civita's work supply the precise formulas for these Christoffel symbols derived from the components of the metric tensor and their derivatives. This equipped mathematicians and physicists with a concrete instrument for calculating covariant derivatives and executing parallel transport within any curved space characterized by metric. The advent of the Levi-Civita connection brought about a revolution in differential geometry, supplying the essential element for developing a comprehensive calculus on curved manifolds. With a rigorous definition of covariant differentiation, curvature could now be defined in a coordinate-independent fashion. The curvature tensor, quantifying the deviation of parallel transport around an infinitesimal loop from the initial orientation, found an elegant expression through the Levi-Civita connection. This tensor offers a complete description of the intrinsic curvature of the manifold at each point, a property that remains unaffected by the manifolds embedding within a higher-dimensional flat space. Moreover, the Levi-Civita connection furnishes a mathematical structure for defining geodesics. Geodesics represent the extension of straight lines to curved spaces, signifying the paths that minimize distance between 2 points. Equivalently, they are the paths along which a vector, when parallel transported along the path, retains its direction relative to the path. Formally, a geodesic is a curve whose tangent vector undergoes parallel transport along the curve itself. The equation governing geodesics is articulated using the Levi-Civita connection, thereby enabling the calculation of these straightest paths in any curved geometry. The concept of the Levi-Civita connection, alongside its associated covariant differentiation, stands as a fundamental pillar of contemporary differential geometry. These elements provide the indispensable instruments for scrutinizing the geometric attributes of curved spaces, encompassing their local curvature and the global structure delineated by their geodesics. This framework is indispensable in numerous areas of mathematics and physics. Its modern relevance extends across vast intellectual landscapes. In pure mathematics, the study of Riemannian geometry, which relies entirely on the metric and its unique connection, is a vibrant field with deep connections to topology, analysis, and algebra. The Levi-Civita connection is the standard tool employed in research on manifold theory, geometric analysis, and the study of curvature properties of abstract spaces. In theoretical physics, the Levi-Civita connection plays a fundamental role, is the indispensable tool for understanding gravity within the framework of Einstein's general theory of relativity. In this theory, gravity is understood entirely as a manifestation of the curvature of spacetime. The geometry of spacetime is described by metric tensor, and the dynamics of particles and light are governed by the principle that they follow geodesics in this curved spacetime. The Levi-Civita connection, uniquely determined by the spacetime metric, is the mathematical structure that defines these geodesics and allows for the covariant formulation of the field equations that relate the curvature of spacetime to the distribution of energy and momentum within it. Without Levi-Civita's rigorous formalization of parallel transport and the connection, Einstein would have lacked the precise mathematical language required to articulate his revolutionary vision of gravity. The connection provides provides the means to compare vectors and tensors at different points in spacetime, a necessary operation for formulating physical laws in a covariant, frame-independent manner. This geometric tool provides the foundation for calculating observable effects like the bending of light by gravitational fields or the precession of planetary orbits, phenomena explained by the curvature of spacetime defined by the Levi-Civita connection. Its enduring impact underscores the power of abstract mathematical concepts to unlock the deepest secrets of the physical universe. The early years of the 20th century presented physicists with a profound intellectual quandary. Newton's venerable theory of universal gravitation, a cornerstone of physical understanding for centuries, described gravity as a force acting instantaneously across vast distances. This framework, immensely successful in explaining planetary motion, presented a significant theoretical challenge when reconciled with the emerging insights of special relativity, which established a cosmic speed limit, the speed of light, and fundamentally altered conceptions of space and time. A new description of gravity was necessary, one compatible with the relativistic structure of spacetime. Albert Einstein, wrestling with this problem for years, developed the revolutionary idea that gravity was a manifestation of the curvature of spacetime itself. Massive objects warp the fabric of spacetime around them, and other objects, including light, simply follow the straightest possible paths, or geodesics, within this curved geometry. This was a radical departure from the Newtonian view. However, translating this profound physical intuition into a precise, quantitative theory required a sophisticated, mathematical language capable of describing geometry in curved spaces in a manner independent of the specific coordinate system chosen to map that space. Laws of physics, Einstein reasoned, should hold true regardless of how an observer chooses to label points in spacetime. This principle of general covariance demanded a mathematical framework that could express physical quantities and relationships in a form invariant under arbitrary coordinate transformations. Enter the absolute differential calculus, a powerful machinery developed by Gregorio Ricciacarbastro and significantly refined and popularized by his student Tullio Levi-Civita. This calculus provided precisely the geometric language Einstein desperately needed. At its heart lay the tensor, a mathematical object that represents physical quantities in a way that transforms predictably and consistently under changes of coordinates. Vectors are simple examples of tensors, but the calculus extended to more complex entities representing stress, strain, curvature, and other physical properties. The ability to work with tensors allowed physicists to formulate equations that held true in any coordinate system, fulfilling the requirement of general covariance. Levi-Civita's crucial contribution within this framework was his exhaustive treatment and clarification of the parallel transport of vectors in curved manifolds, a concept fundamental to defining derivatives and curvature in such spaces. In flat Euclidean space, moving a vector parallel to itself is straightforward. Its components remain unchanged. In a curved space, however, the direction of a vector changes as it is moved along a path, even if one attempts to keep it pointing the same way relative to the local geometry. Levi-Civita rigorously formalized this notion, introducing the concept of the affine connection. The connection, often represented by coefficients known as Christoffel symbols, a term coined by Ricciacarbastro, allows one to define how vectors change as they're transported infinitesimally from one point to another. This provides the mathematical basis for the covariant derivative, a generalization of the standard derivative that accounts for the curvature of the space. The covariant derivative of a tensor measures how the tensor changes intrinsically, independent of the coordinate system used. This formalization of parallel transport and the covariant derivative was indispensable for defining curvature in a rigorous, coordinate-independent way. The Riemann curvature tensor, a central object in differential geometry, quantifies the curvature of a manifold. It can be expressed elegantly using the connection coefficients and their derivatives. Various contractions of the Riemann tensor yield other important tensors, such as the Ricci tensor and the scalar curvature, which provide measures of average curvature at a point. These tensors, objects of pure geometry, became the building blocks for Einstein's theory of gravity. Einstein's physical insight was to equate the geometry of spacetime with the distribution of mass and energy. Within it, he proposed that the curvature of spacetime, as captured by the Ricci tensor and the scalar curvature, was directly proportional to the stress-energy tensor, which describes the density and flow of energy and momentum. The resulting equation, known as Einstein's field equation, r sub mu nu minus 1/2 g sub mu nu or equals 8 pi g over c to the power 4 t sub mu nu, where r sub mu nu represents the Ricci tensor, g sub mu nu the metric tensor, or the scalar curvature, t sub mu nu the stress-energy tensor, g Newton's gravitational constant, c the speed of light, expresses this fundamental relationship. The formulation of this equation in a generally covariant form was possible because the mathematical tools provided by the absolute differential calculus, particularly the covariant derivative and the tensors derived from it, were available. Levi-Civita's role involved providing the tools and engaging directly with Einstein on the mathematical intricacies of the nascent theory. Their correspondence, particularly in the years leading up to the final publication of General Relativity in 1915, is legendary. Einstein, a brilliant physicist, but relatively less steeped in the formalisms of advanced differential geometry, relied on Levi-Civita's expertise to navigate the complexities of tensor calculus. Levi-Civita pointed out errors in Einstein's initial attempts to formulate covariant field equations and guided him toward the correct mathematical framework. One famous anecdote recounts Levi-Civita identifying a mistake in Einstein's use of the covariant derivative, a correction Einstein readily acknowledged, referring to Levi-Civita's letters as illuminating. This intellectual exchange highlights the collaborative nature of scientific progress and the critical dependence of groundbreaking physical theories on the availability of appropriate mathematical structures. Levi-Civita's clear explanations and rigorous approach solidified the mathematical foundation upon which general relativity was built. The impact of this work resonates profoundly in contemporary physics. General relativity, formulated using the tensor calculus refined by Levi-Civita, remains our most accurate description of gravity. It is the theoretical bedrock for understanding phenomena ranging from the behavior of black holes and the expansion of the universe to the subtle gravitational effects used in GPS technology. The equations, derived from Einstein's field equation, solved using the machinery of differential geometry and tensor analysis, predict gravitational waves, ripples in spacetime that were directly detected a century after Einstein's prediction. Cosmological models describing the evolution of the universe from the Big Bang rely entirely on the framework of general relativity. The mathematical language provided by Levi-Civita and Ricciacarbastro proved so powerful and versatile that it transcended its initial application in relativity. It became a standard tool in various fields of physics and mathematics, wherever curved spaces or coordinate-independent formulations are necessary. The concept of the connection, in particular, evolved into a central theme in modern differential geometry and theoretical physics, underpinning gauge theories and fiber bundles. Levi-Civita's contribution to general relativity was foundational. He provided the indispensable mathematical grammar and syntax, the tensor calculus, and the theory of connections that allowed Einstein to write down the sentences of his revolutionary new physics. The abstract geometric concepts he refined became the concrete language of spacetime curvature, allowing physicists to describe gravity as a geometric property of the universe rather than a mysterious force. This confluence of physical insight and mathematical rigor yielded a theory of unparalleled elegance and predictive power. The elegance and utility of these geometric methods, so powerful in describing the curvature of spacetime, were emblematic of a broader approach Levi-Civita took in his scientific endeavors. His facility with sophisticated mathematical techniques extended across diverse areas of physics and applied mathematics, enabling them to tackle complex problems in fields seemingly distant from the abstract geometry of relativity. His investigations into the behavior of fluids, for instance, would demonstrate a similar capacity to bring powerful analytical tools to bear on challenging physical phenomena. Tullio Levi-Civita possessed an analytical breadth that propelled him into the equally complex domain of fluid mechanics. His investigations into the behavior of fluids, for instance, would demonstrate a similar capacity to bring powerful analytical tools to bear on challenging physical phenomena. The study of fluids, encompassing everything from the gentle flow of water in a channel to the violent churn of turbulent eddies, presented physicists and mathematicians of his era with formidable obstacles. The fundamental equations governing fluid motion, such as the Navier-Stokes equations, had been formulated, yet deriving exact solutions for realistic scenarios proved exceedingly difficult. These equations, representing conservation of momentum and mass, form a system of coupled partial differential equations, often nonlinear, whose complexity frequently defied direct analytical attack. Understanding phenomena like wave propagation on surfaces, the formation and persistence of vortices, or the drag experienced by objects moving through a fluid required simplifying assumptions or numerical approximations, methods that offered valuable insights but often lacked the definitive precision of an exact mathematical solution. The quest for such exact solutions, even for idealized fluid models like viscid or incompressible flows, remained a significant challenge, offering benchmarks for theoretical understanding and practical application. Levi-Civita approached these problems with the same rigor and mathematical sophistication he applied to differential geometry. He recognized that while the full complexity of fluid motion might be analytically intractable, specific, important cases could yield to the power of sophisticated mathematical techniques. His work in fluid mechanics drew heavily upon methods from complex analysis and the theory of integral equations, tools well suited to tackling boundary value problems and deriving exact forms for flow fields under specific conditions. He sought to uncover the underlying mathematical structure of particular fluid behaviors, providing precise descriptions where only approximations or qualitative observations had previously existed. His contributions illuminated several key areas within hydrodynamics, providing foundational results and demonstrating the efficacy of advanced analytical methods. One particularly significant area of his work concerned the theory of vortices. Vortices, swirling regions within a fluid, play a crucial role in phenomena ranging from atmospheric dynamics to the lift generated by airplane wings. Understanding their behavior, stability, and interaction was and remains a central problem in fluid dynamics. Building upon earlier work, notably by Gustav Kirchhoff, Levi-Civita made fundamental contributions to the theory of free vortices, those regions of concentrated vorticity embedded within an otherwise irrotational flow. Kirchhoff had derived equations describing the equilibrium shapes of a single, uniform vortex patch in a plane. Levi-Civita extended this theory, investigating the stability of these shapes and examining more complex configurations. He employed techniques rooted in conformal mapping and integral equations to analyze the boundary shapes of these vortex regions. For example, he studied the stability of the Kirchhoff ellipse, a specific elliptical shape a uniform vortex patch can assume. His analysis revealed conditions under which this elliptical vortex would maintain its form or instead become unstable and potentially break apart, a result with implications for understanding the dynamics of vortical structures in various physical systems. Beyond analyzing existing vortex models, Levi-Civita also developed new theoretical frameworks for understanding vortex dynamics. His work included investigations into the motion of systems of point vortices, idealized representations of concentrated vorticity. While point vortex models simplify the complex internal structure of real vortices, they provide valuable insights into the collective behavior and interactions of vortical elements, particularly in two-dimensional flows. Levi-Civita's thorough mathematical examination of these systems aided in creating analytical approaches for forecasting their paths and stability, a subject of ongoing investigation. The mathematical sophistication of these vortex solutions, frequently conveyed through elaborate functions originating from complex analysis, offered infrequent examples of precise descriptions for particular yet physically pertinent fluid movements. Levi-Civita also applied his analytical expertise to the investigation of fluid waves, specifically surface waves on liquids. The movement of waves on water surfaces affected by gravity and surface tension represents a foundational challenge in fluid dynamics, defined by its nonlinearity and dispersion. While simplified linear theories were available, capturing the complete intricacy of wave shapes, especially those with considerable height, necessitated more advanced mathematical instruments. Levi-Civita addressed the challenge of identifying the precise form of steady, irrotational gravity waves of finite amplitude on deep water. Employing complex variable techniques, he succeeded in deriving a parametric representation for the wave's contour, a notable accomplishment considering the problem's nonlinear character. This research yielded one of the initial exact solutions for a finite amplitude wave problem, serving as a reference point for evaluating approximate theories and illustrating the feasibility of exact analytical resolutions for certain nonlinear fluid occurrences. His methodology involved transforming the fluid region in the physical plane to a more straightforward region in a modified complex plane, a customary practice in complex analysis applied with considerable proficiency to this particular challenge. The boundary conditions, especially the dynamic condition at the free surface that equates pressure to a constant value, translated into complex mathematical stipulations within the transformed plane, resolving the resultant boundary value problem, frequently involving integral equations, enabled him to ascertain the exact configuration of the mapping function and, consequently, the precise shape of the wave profile. This analytical success provided profound understanding into the potential forms of stable, propagating waves, revealing specifics about their peaks and troughs that linear theories could only approximate. The influence of Levi-Civita's contributions to hydrodynamics extended past these particular resolutions. His stringent application of sophisticated mathematical procedures established a benchmark for analytical inquiry in the discipline. He showcased the potency of complex analysis, integral equations, and potential theory in resolving difficult problems where simple methods proved insufficient. His exact solutions for vortex shapes and wave profiles served as crucial test cases for validating approximate methods in numerical simulations. They provided a theoretical foundation for understanding specific fluid phenomena with unparalleled precision. The methods he employed and refined became part of the standard toolkit for researchers in fluid dynamics, influencing subsequent generations of mathematicians and physicists working on similar problems. The study of turbulence and highly complex flows often requires numerical or statistical approaches, and the pursuit of exact solutions for idealized cases, initiated and advanced by figures like Levi-Civita, continues to offer fundamental insights into the underlying mathematical physics of fluid motion. His contributions underscored the profound connection between abstract mathematical theory and the concrete description of physical reality, a theme that resonated throughout his career and would continue to shape his later investigations and his lasting influence on the mathematical community. As the 20th century progressed, Tullio Levi-Civita's intellectual trajectory turned towards consolidating and refining the powerful analytical machinery he had helped forge. His later research represented a deepening of his methodological rigor and an expansion of its application to complex physical systems, particularly in celestial mechanics. The intellectual landscape of the time was grappling with the intricate dynamics of planetary motion and the stability of gravitational systems, problems that demanded ever more sophisticated mathematical tools. Existing theories, while powerful, often encountered limitations when faced with the sheer complexity of multi-body interactions and the subtle perturbations that govern celestial orbits. Levi-Civita's approach to these challenges was characterized by an unwavering commitment to analytical precision and a profound geometric intuition. He sought to develop a more unified and elegant framework for understanding these intricate dynamical systems. His work in this period involved a comprehensive re-examination of classical mechanics, particularly the Hamiltonian formulation and its extension using the covariant methods he had pioneered. The problem was, in essence, to render the unwieldy equations of celestial mechanics into a form that revealed their underlying geometric structure, thereby facilitating deeper analytical insights and more robust predictions. He meticulously worked to express the laws of motion and the behavior of gravitational potentials in a coordinate-independent manner. This involved the careful application of tensor analysis to the equations governing the motion of celestial bodies. For instance, in his investigations into the three-body problem, a notoriously intractable issue in classical physics, Levi-Civita sought to identify conserved quantities and to understand the qualitative behavior of solutions through their geometric properties rather than solely relying on direct integration, which was often impossible. He explored transformations of variables and canonical transformations that could simplify the problem or reveal his symmetries. His work on the restricted three-body problem, for example, delved into the geometry of phase space and the nature of periodic orbits and their stability. A significant aspect of his later contributions was the development of what is now recognized as the Levi-Civita connection, a fundamental concept in differential geometry that provides a way to differentiate vector fields along curves in a way that is independent of the chosen coordinate system. While its initial formulation was deeply tied to the geometric interpretation of his tensor calculus, its implications extended far beyond. In the context of celestial mechanics, this connection allowed for consistent and rigorous treatment of curvature in the curved spacetime of general relativity. But even within the framework of Newtonian gravity, it offered a powerful way to handle the complexities of gravitational potentials and their derivatives in a covariant manner. This meant that the physical laws remained invariant regardless of the observer's reference frame, a principle of paramount importance in physics. His methodological rigor was evident in the clarity and elegance of his mathematical exposition. He believed that a truly profound mathematical idea should be expressible in a way that is both precise and intellectually accessible, even if the underlying concepts were advanced. This commitment to clarity influenced his teaching and his mentorship. He cultivated a generation of mathematicians and physicists who inherited his dedication to rigorous analytical methods and his appreciation for the geometric underpinnings of physical laws. His lecture notes and treatises from this period served as foundational texts, guiding students through the complexities of analytical mechanics and differential geometry with the clarity that was his hallmark. The problem of formulating the laws of physics in a manner that respected the fundamental symmetries of spacetime and the nature of motion itself was a driving force. Levi-Civita's unique solution lay in his ability to synthesize abstract mathematical concepts with concrete physical problems. He saw the mathematical structures as embodiments of the physical reality they described. For celestial mechanics, this meant understanding the orbits of planets as geodesics in a geometric space whose curvature was dictated by the distribution of mass. The modern relevance of this aspect of Levi-Civita's work is profound. The emphasis he placed on analytical rigor and geometric intuition remains central to advanced mathematical physics. Concepts like the Levi-Civita connection are indispensable in general relativity, where they describe how vectors change as they are transported along curves in curved spacetime. Furthermore, his meticulous approach to formulating dynamical systems continues to inform research in areas ranging from astrophysics to the study of chaotic systems. The pursuit of elegant, invariant formulations of physical laws, a principle he championed, is a guiding star for physicists grappling with the most profound questions about the universe. His legacy in this later phase of his career is in the enduring methodology he refined and transmitted, a methodology that continues to shape the very way we think about and describe the physical world. His intellectual rigor provided a bedrock upon which much of modern theoretical physics would be built, ensuring that the pursuit of understanding was always grounded in the most precise and insightful mathematical language. The intellectual framework Tullio Levi-Civita bequeathed to the scientific world extends far beyond the specific equations he formulated or the theorems he proved. His work in differential geometry and tensor calculus provided the essential lexicon for describing the intricate curvature of spacetime, a concept that would fundamentally alter our comprehension of gravity. The invariant nature of this tensor calculus offered a universal language capable of expressing physical laws in a manner that remained consistent regardless of the observer's frame of reference. This invariance was an elegant mathematical property and a profound insight into the objective reality of physical phenomena, a reality that persists even as our perspective shifts. The Levi-Civita connection, a cornerstone of his geometric explorations, illuminates how geometric quantities evolve as they traverse the landscape of curved space. In the context of Einstein's general relativity, these connections are indispensable, detailing the transformation of vectors as they are parallel transported along paths within a curved spacetime. This mathematical machinery allows for the precise description of how mass and energy warp the fabric of the universe, dictating the motion of celestial bodies and the very passage of time. The beauty of this formulation lies in its ability to capture the essence of gravitational interaction as a manifestation of geometry itself. Furthermore, Levi-Civita's meticulous approach to formulating dynamical systems continues to inform research across a remarkable spectrum of scientific inquiry, from the grand scales of astrophysics, where the orbits of planets and galaxies are governed by gravitational fields, to the intricate study of chaotic systems in fluid mechanics and beyond. His methods offer powerful tools for analysis. The pursuit of elegant, invariant formulations of physical laws, a principle he championed throughout his career, remains a guiding star for physicists grappling with the most profound questions about the universe. This enduring quest for unifying principles, expressed through the rigorous language of mathematics, reflects a deep-seated belief in the underlying order and intelligibility of the cosmos. His legacy resides fundamentally in the enduring methodology he refined and transmitted. This methodology, characterized by its emphasis on geometric intuition and the power of invariant analysis, continues to shape the very way we think about and describe the physical world. It provided a bedrock upon which much of modern theoretical physics would be built, ensuring that the pursuit of understanding was always grounded in the most precise and insightful mathematical language. The elegance with which he wove together geometry and physics created a paradigm shift, enabling a deeper, more unified understanding of the fundamental forces and structures that govern existence. The impact of his work resonates in countless areas. In the realm of celestial mechanics, the precise description of orbital paths, the behavior of tidal forces, and the dynamics of rotation levitating bodies all owe a debt to his geometric insights in fluid dynamics. His contributions to the understanding of turbulence, viscosity, and wave propagation laid groundwork for subsequent generations of researchers. The very concept of a connection in differential geometry, a generalization of the idea of parallel transport, has become a fundamental tool in numerous branches of mathematics and physics, from the study of fiber bundles and topology to the formulation of gauge theories in particle physics. The universality of his tensor calculus, his ability to express physical laws in a form independent of coordinate systems, proved crucial for the development of general relativity. Einstein himself recognized the profound utility of Levi-Civita's mathematical innovations, integrating them into the very fabric of his revolutionary theory of gravity. This collaboration, though largely through shared mathematical language rather than direct personal interaction, stands as a testament to the power of ideas to transcend disciplinary boundaries and to the enduring influence of a mathematician who provided the tools to unlock the secrets of the universe. His work offered a clarity and precision that allowed physicists to move beyond Newtonian approximations and to grasp the more subtle and complex reality of the dynamic, curved spacetime. The intellectual rigor he embodied, the relentless pursuit of clarity and truth through mathematical reasoning, serves as an inspiration. His life's work stands as a powerful reminder that the most profound scientific discoveries are often forged at the intersection of abstract mathematical thought and the concrete observation of the natural world. Tullio Levi-Civita's enduring contribution lies in the seamless integration in his creation of a mathematical language that described the universe and revealed its inherent geometric beauty and underlying order. His legacy is etched in theorems and equations, and in the very way we perceive and interpret the cosmos, a testament to a mind that truly illuminated the universe through the power of mathematics.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.